Thank you, Dr. Madhukan. First, I would like to give big thanks for this organizer, especially Dr. Madhu, who are giving me opportunity to talk to the mathematicians. I mean, after a long time, I'm talking to the in a mathematics conference, and I'm working mostly on the cloud physics and AI/ML things. So I'm a little bit away from the mathematics research side, but I'm applying the mathematics. And in this talk, actually, it is not a modeling, weather forecasting model, but it is something the smallest scale which we do at the academic level. We generally do the direct numerical simulation. So I'm connecting this direct numerical simulation we have done in the studying the cloud microphysics. So what is the cloud microphysics and how it is connected to the weather forecasting model? That is the part. And what is the role of turbulence? Since it is an atmospheric flow, so always we have to talk about the turbulence. And what is the application of direct numerical simulation in different kinds of the study in the cloud microphysics, and how it can give some information to the large scale models. That is the part. In terms of the mathematics, I will just tell the model which I have used, some PD like Navier stable equations and some set of the differential equations for the basically particles in a turbulence, that you can say. So these particles are the cloud droplets in this case. So I will start with the overview of okay, can you see the slide, changing the slide?
Yes.
Okay, so as we said about the global models, so like the climate or weather forecasting models, so those models are really doing the simulation for the big area, like either the whole globe or some continents or country, and they do a lot of parameterization for different parts during the simulation. So because we cannot solve everything at a small scale, so that's why the parameterization has been done. So one of the parameterization is the cloud physics, and the clouds are one of the parameterization part. So if you see here, so this is something like a domain. Suppose we want to consider a particular area, any in the globe. So when you see the globe, every time in the globe we see there are some clouds. So when we are going to do any kind of the weather forecasting and all, we have to think about the cloud because they are changing the weather. So changing the weather in a different way. So there are so many things, the microphysical process inside the cloud and like radiations and all. So, but when you see the cloud, there is a different height of the cloud. There is different level of the cloud. The highest level you can see here. This is what is the very high level cirrus cloud. Then there is a middle level cloud. There are some nomenclature for that. It's called the stratocumulus cloud. And the lower level cloud is called the cumulus cloud, which is what we are mostly worry about in terms of the rainfall or in terms of the precipitation and other local variable, local weather conditions. So this low level cloud, which generally we see every day from our naked eyes, in the like this is a picture for a cloud in a clear sky. So in this cloud, actually, a lot of microphysics processes happening at a smallest scale or a small scale, which is not resolved in the large scale models. So for those small scale things, we can do at a small scale simulation. So in the small scale simulation, we are talking about the direct numerical simulation, which is basically the smallest scale. And what I am going to focus today is the three main components. One is the cloud microphysics, which is basically involving the cloud droplets. So that is how the cloud entrainment and mixing is happening in the cloud, and how the droplet size structure changes. So if you just come back to this figure, so here this is the very nice cloud, but you see the cloud edges. This is the environmental air, and this is entering inside the cloud, and that will change the cloud property. That can change the cloud lifetime as well. whether the cloud droplets will stay or they will evaporate or they will condense depending on the environmental condition. And that gives the information for the forecasting. So, but what is happening at the small scale, that is not known. And the study of the droplet spectra, that is the main important factor in the simulation of the weather forecasting. And second aspect is just come below the cloud droplet, I mean on one level down. So this is the aerosol activation dynamics. So before the cloud droplet, before any cloud droplet, there are aerosols. Aerosols always available in the atmosphere. From the aerosol, it becomes the cloud condensation nuclei, and that becomes the cloud droplet. That becomes then becomes the raindrop, and after the rain, it starts precipitation. Okay, so all these things happens in a turbulence environment. You know, atmospheric flow is really highly turbulence. Cloud is the very high turbulence flow. So we will also do. We have done some study for the evolution of the kinetic energy, turbulent kinetic energy, dissipation rate, all these kind of flow property, turbulent flow property. So I will give some overview of these three topics in this talk. So I will start with our weather forecasting models. So if you see any general circulation model which is used for the weather forecasting, it generally has the three parts: Gaussian model, atmospheric model, and land surface. So I am going to talk about the atmospheric, in particular the atmospheric physics, and I will also say that atmospheric chemistry, where is the aerosol. Basically, I am talking about the microphysics, which is related to the aerosol dynamics as well. And my idea is to go to the small scale large utility simulation and the direct numerical simulation. So I'm focusing on the direct numerical simulation as I give the title of this talk. So first I will just tell about what are the mathematical equations here. So this is the only slide where I will talk about the pure mathematics part, and later on I'm going just for the methods and the application and physics only, hardcore physics. So if you see, we have the two different set of the equations. The red color is the Eulerian frame, where we are solving the flow on the grid, and we have the velocity, solving the velocity, and we are having the humidity, like vapor mixing ratio, and the temperature. So these are the flow variable we are solving on the Eulerian grid. And apart from that, when we have this flow, this is basically a turbulent flow. And we on the turbulent flow, we have the cloud droplet, which is for the particles, we can say. So for the cloud droplets or particles, we have to calculate their velocity using the flow, the U, and the size of each particle, because size matters, that is the cloud droplets, and the position of the cloud droplets, and the supersaturation. Supersaturation is responsible for the growth of the cloud droplets. This is very general way, and it's a very stable theory about it, and we have done a lot of people have done a lot of work on this. So overall, I am saying that in terms of the particle physics, you can say that it is a particles in the turbulence, but we are applying into the atmospheric science. So this is a cloud turbulence and the cloud droplets we are simulating. Okay, so for solving this, we have a pseudo-spectral method, and we are using the periodic boundary conditions. So we always take a cubic domain. Since it is a turbulent flow, so initially we have to give some initial condition as a turbulent flow. So we are running this only this model, first Eulerian part, generating a turbulent flow, which is basically stationary turbulent flow, and homogeneous isotropic flow we are taking here. So this is the way that we are initially running the simulation for 10 to 15 seconds and get a stationary state, and then we provide into the domain. So this is something the initial conditions we are giving for the flow part. After the flow part, we have the cloud droplet. So initially we are giving some number of the cloud droplets based on the number density which we generally observe in the real clouds. Observation can be the ground observation or the flight observation. So there is a standard way, or there is a actual observation how much number density within a per centimeter cube. So what is the droplet in per centimeter cube? Based on that, we calculate the total number of the droplets and we give into the domain. So this picture is basically, this figure is showing that this is the study of the entrainment and mixing. So this is a whole cubic domain, and in between I'm creating a cloud slab. And here, once the simulation happens, the cloudy air, the warm air, the environment air is basically going inside the cool air. The cloudy air is the cool air because it's water droplets. So cloud droplets we are considering as a spherical particle of the pure water. There is no other salt inside. So this is what the initial conditions we are giving. And now you think about the computational details. So as I said, I'm solving using the pseudo-structural method, and I will come to the point of what the numerical scheme is there. So first, I'm talking about the whole domain is really very highly computational. So generally, we are doing the simulation in a centimeter domain. We can go up to the 1 meter domain. So we can go 25 centimeter, 50 centimeter, or 1 meter cube. That is enough. So have very high computation. But the domain, the grid size is 1 millimeter, and this is based on the turbulence Kolmogorov scale. So it is coming up to the 1 millimeter. So in this case, if you see that we will get at least 1024 cube grid points. It's huge. So we cannot run on a simple PC or workstation. So we go for parallel computer HPC, and we have to divide the domain. So the domain decomposition is happening in the 2D processor topology. All these are very standard technology. I just am telling here everything how we are applying in our cloud physics. So in this case, Y and Z direction data is broken, and the X direction data is kept as it is. So this 0 to 16, these are the processors in dividing into the 2D processor topology. Each processor is getting the whole X direction, which we call number of particles in the grid points in the X direction, and Y and Z direction divided. So the whole one processor is getting this kind of slab or cuboid. This is called the pencil in terms of the HPC technology, parallel technology. So one pencil is with the each processor, but whatever the data they have, the grid points, grid values, and the particle values, they are totally independent from the other processor. So they don't know what the next processor or the neighboring processor has. And now we are, after discretizing it, we are solving. After applying this discretization, we are applying the second order scheme here. Second order is we are applying that is enough, and and there's too much computational expensive, so we did not go to the higher order scheme. But if you see here in this just a second order predictor corrector scheme, in this case, first we have all this initial setup what I have shown. Then we are solving the fluid flow properties, the variables at the grid points, and the droplets are inside the grids. Suppose there is a grid, if you say that these are the grid, and droplets are inside the grid. They are very tiny droplets in the micron. So within the 1 millimeter grid, there are many droplets. So when we update the position, in this case, when we update the position of any droplets, they can change their location. So suppose they are in the processor 0, they can go to the 2, 1, 3, anywhere. So every time in this second order step, whenever we are updating the position of the particles or droplets, we need to do some kind of exchange among the processor. So like this guy, this was very near to the boundary of the second processor. It may move to the second processor. So it came from here to this second processor. So this kind of processor communication, inter-processor communication, we have to do 2 times in a one-time iteration. And in fact, the time step is very low here. It's like very small. It's like 0.001 into 10 to the power -4 or -3 it goes. Generally, it is -4. So it is really every time step we have to do 2 times this kind of communication. This is all communication happening in the real space when we are talking about the particle action, and whatever the communication is happening in the Fourier mode, that is the point-to-point communication, all-to-all communication, that always there. This is what the property or drawback or whatever we say in the pseudo-spectral method. Okay, so this is what the numerical scheme I am saying. Now, why I discuss all this complexity? Because I am talking about a DNS which is can be done in a sub-meter domain, in some centimeters. think about the real cloud, which is really in many kilometers. How we can study? So the question is that how big domain we can simulate in our computer, in our HPC. We have done some kind of work. This is the work what I am telling the whole journey for last 1 decade. What has been done in the using the DNS in the cloud microphysics. So we started working initially like a 25 centimeter domain, then 50 centimeter cube domain, 1 meter cube domain. It's okay, but still 1 meter cube domain, what we are getting? If you talk about the turbulence below, there are the eddies, and eddies are really big in the real cloud. They are in the kilometers in a particular cloud, or even bigger than in the tens of the kilometer. So when we are simulating the things, if you see that the properties are changing when we are changing the domain size, because the eddy we are resolving the bigger and bigger eddies. But the question is that how big domain we can go. We cannot resolve, we cannot do the simulation as DNS for the kilometer. So there is a way that what DNS can basically provide, where it can provide the information so that we can improve our weather forecasting model. So the first step is that after the DNS there is a large eddy simulation. So large eddy simulation domain can go in the few kilometers or maybe the hundreds of kilometers, but the smaller can go in few kilometers, and their grid size can come down up to the 10 meter, or maybe sometimes people are doing 5 meter also nowadays. Now we have the HPCs available. So what I am saying that here in this case there are a lot of parameterization happens. Even they don't know what is the cloud size, droplet size distribution we should give for the each grid depending on the location of the grid. So if we can do a simulation of the in the DNS up to a grid size of the LES, then it will be a really a good contribution. Like we can provide a seamless information to the large eddy simulations, and we can improve the LES study. But is it possible? Can we do? We have gone up to the 1 meter cube, and that is also really very difficult. So if you go for 4 meter or 5 meter, in case of the 4 meter cube, if we resolve up to the dissipation scale on the Kolmogorov scale, that is 1 millimeter, so we will have at least 4,000 cube grid cells, and we take the natural number density, that the billions of the droplets, and really 10 to the power minus 4 of the time step. So think about how much time it will take and how big computational power we need. So this is really difficult. One thing is computationally, and second thing is the storage purpose. So we have tried this 4 meter cube, just starting running something and generating the initial condition. The one particular file for the Eulerian field goes 2.7 terabytes. And doing such kind of writing or reading such kind of files is requires too much like a IO time. So just if you see the number, just first time we are writing this file, it was taking 4 hours to write one particular file. Okay, so it is all really very complex to do the simulation in the bigger domain. Well, so this is all the complexity. Now I move to that. See the complexity, how it is happening. So we did some kind of comparison, comparative study whether we can go to the 4 meter cube or not. So we started doing the simulation in the 12.8 centimeter cube and went into the 2 meter cube. So we set the domain D1 to D5, and then we calculated the time for the 60,000 iterations using only 1024 cores. It's not only 1024 cores available for the many days, is difficult to get that much HPC time. So if you see that from D1 is a small domain, if we go to the bigger one, D2 domain 25 centimeter, it takes 4 times more extra times computational times. And then if you go for the D3, it goes 1.5 times more. Like that, if you go to the 2 meter cube, it is going 12 times. But if you compare, 12 times bigger than the previous domain. But if you compare from the smallest domain, it is going 2,500 times more. And at the same time, when you are increasing the domain, you have to increase the droplets. So the way the droplets are increasing, it is going into the billions. So if we say this second, they convert into the days, it is saying that the 2 meter cube domain will take 80 days if you do, but this is the simulations, approximation I have done maybe 2-3 years before using the 1024 course, but on the very latest processor, I think Broadwell processor, which we still have now. So what is the requirement we need, like 16,000? If we see the projection here, I'm just making some projection. We have to go to the 23 times if we want to go for the 4 meter cube. But the good news is that we have done some kind of scaling in this particular code, what we have, say like a hybrid code. So here, if we are saying that if we want to go 51 centimeter cube, so if we take the 1024 course, then it is like a optimized, we are reaching near to the ideal condition. And even we are getting sometimes of the super linear speed up. But this is all up to the half meter or 1 meter cube. We can go for that, but how much time it is taking, that is different. That time is given in this table. So if we want to go even bigger domain, what we wanted to do for the giving contribution to the LES, we have to go even bigger 4 meter cube. So this is something the projection we have done a few years before, but still we could not succeed to do a full simulation of the 4 meter cube because we never get that much time in the HPC. HPC is busy generally for the weather forecasting. Anyway, whatever the work we have done, so I'm telling this story for the last 1 decade. What we have contributed by doing the DNS and how we contributed to the cloud community in the cloud physics. So first thing is we have calculated some 10 years before we did this simulation in a small domain like a half a meter cube or 25 centimeter cube. First thing we have calculated the phase relaxation time. So there is a theoretical formula in the literature, but nobody knows whether we can get the same kind of validation from the numerical simulation or not. So we have done many experiments long back. So taking the different size of the droplets and different size of the number density, different number density, so taking the smaller number density to the higher number density. And then we verified from the actual formula and we will do the estimation, and we found that yes, this DNS, which we are doing the 3D DNS with all kind of variables solving, there is no approximation, nothing, no parameterization, then we are really reaching to the theory. So we can validate our model results with the theoretical formulas. So this is the work done 10 years before and published in the Theoretical and Computational Fluid Dynamics, and it was a really very good information. So people know what is the phase relaxation time. So what is the meaning here? So when I'm talking about the cloud, any time in the cloud, either this mixing happens, so they do mixing, either it is evaporation or condensation happens. But we need to know that when there is a stationary state, when there is a relaxation, so the relaxation means that time the cloud droplets are neither increasing nor decreasing, no evaporation, no condensation. So it happens sometimes. So what is that particular time within a particular environmental conditions? That information was not available, and this is the information we have provided using this our DNS simulation. So this was a really good information for the cloud study. Second thing, when you talk about the mixing can change anytime. Environment condition can change anytime. In the seconds or in the minutes, whatever temperature right now, it can change in the after 1 hour or after 10 minutes. So that when the mixing happens, it do the process of the condensation and evaporation of the cloud droplets. So in the normal conditions, this is what we have the droplet growth equation, what I have shown in the previous slide. So here this is a supersaturation, this is a growth constant which depends on the thermodynamic parameters. And suppose this is the value. But when we give any initial condition, we will give just one particular value and we will calculate our droplet size and all. What happens that if the conditions are changing? So we have done the study like suppose there is a less humidity, then the growth will be less and they will not grow, the droplets will not grow and they can evaporate. So this is called something inhomogeneous mixing. So the inhomogeneous mixing means it will evaporate faster. So that means the growth rate will be less. So we have done the experiment when it is 10 times smaller growth rate, 10 times higher growth rate. So what is happening here, I will not go in detail, but I just want to tell in all these three figures, the shape of the PDF is different, the probability distribution function. This shape is important for the cloud space distribution. So in normal condition, it is this, but when it is very humid, it is going to the U shape, okay, or V, the particular V shape. This shape basically gives the information what will happen for the forecasting of the whether it's precipitate or not. This can go, this information they generally approximate in the larger scale model. So this work was done also like 10 years before, and we have we actually told that okay, what will happen in the extreme case in the inhomogeneous and homogeneous mixing. So this is the another application solving these differential equations, and all these things we have done at a particular temperature, that we kept the temperature constant. Later on, after 2 years, we have coded, we made the code in the numerical equation. We have actually coded the temperature equation as well. So then in 2014, we came into the conclusion that this is the overall things what will happen when we have the different kind of scenario like decaying turbulence with a different number density or the stationary turbulence. So basically, as an initial condition, we are giving a stationary isotropic homogeneous turbulence, but based on the environment condition, the turbulence may decay also, or it can increase also, or it may sustain. So we have done two tests. Basically, we want to see what happens in the decaying turbulence when all the turbulent kinetic energy got dissipated, or it sustains. So it depends on the environmental condition, the atmospheric condition. So this is what the information we gave, that this kind of the situation can happen in the decaying. So in the decaying turbulence, lot of complete evaporation happens. The droplets can go up to the zero size. And in this case, when it is really a sustaining, so then a relaxation state comes. So this is what the relaxation process people wanted to know in the all, when the temperature, everything is involved. So this relaxation time gives a lot of information for the cloud lifetime or cloud property. So till now, this paper is published in the Journal of Atmospheric Science. It gives a lot of information that when temperature is improved, what is the role of temperature. Okay, so all those things I have told as a statistical analysis and graphs and all. Now just try to visualize what happens in the DNS domain. So this is suppose I think 1 meter cube domain or maybe half a meter cube domain. So this is the cubic domain, and we are providing the turbulence flow as I said initially, and the gray color is showing the turbulence flow, and then in between we are putting the cloud droplets to create a cloud slab. So this is the simulation I am telling about to study the mixing process. How does this is the environment here, this is the gray color, it will entrain inside the cloud. So if you see any cloud in the sky, you see that there is a white color cloud and then the environment. So that kind of situation we are creating here. So once the simulation starts, if you see that the cloud slab is spreading and the environment air is going inside. So the droplets which are inside the cloud slab, they will keep growing, okay? But the droplets which are going in this area, in the environment area, they will start evaporating. So here the white color is showing the higher humidity or higher supersaturation air, that is the white color. And the blue color is showing the bigger droplets because they have the more water. And the red color droplets are basically the smaller droplets which are evaporating. So this video will tell you that how the droplets are coming this area, they are becoming red, that means they are evaporating. So this is all we have simulated. And if you see that all the droplets which are coming in this area, they are getting red color, and in the white area, they are in the blue color. So they are bigger, they are growing. So this is just for a few seconds simulations, and I just put rotation also. So okay, so this is what is simulation. We have shown the mixing process. Okay, and now we move to the next part. Okay, what is saying? We have done the simulation, we have done the verification, some kind of theory and all. But any numerical simulation, we need to validate either the lab experiment or the observation. So recent, after that, all the simulations, a lot of study, we have started doing comparison with the observation. So one of the observation is the KIPEX experiment, which is happening in the Ministry of Earth Science, especially in the our IITM. It's a KIPEX, is a cloud aerosol interaction in the precipitation enhancement experiment. So here we have our research flight. It goes inside the cloud and it's take the observation and take the observation of the cloud droplet size, spectra, humidity, and the mean size, everything. So in this slide, I am comparing. This is the size spectra, size distribution we have got from the flight, and this is what we are getting from the DNS. Main thing here is to compare whether the shape is coming same or not. So if you see at any height, we are getting almost similar shape. It is really difficult to compare just a small domain in the DNS and comparing with a flight observation, which is like taking the observation in hundreds of the kilometer. But the proofs what we are keeping in the flight, they are taking the information at a very small scale. So if you see that in the minute scales, we are getting the information. So that's why we are able to compare to the smallest scale. And some mean properties like mean radii. So see the shape of the mean radii, the two different observation, and the mean radii what we are getting from our simulation, that is also verified. Similarly, the this one, the sigma, like standard deviation and fluctuations in the number density. All number density is changing here because we are when we are taking the observation, the flight goes very fast. So it is not considering the small scale fluctuation which we can capture in the numerical simulation. So this is the comparison from the observation. Another way of comparing is some other statistical method and properties like probability density function with the relation of the different property. Yes. Hello.
Yeah, Meghna, do you have any questions? Okay, maybe it is unmuted due to some technical problem.
Okay.
Yeah, please go ahead.
Okay, so I'm just saying that we have done this DNS and whatever the numerical simulation we got, we are comparing with the field observation. So all this study, what I have talked, it is about the cloud droplets. So when we talk about the cloud droplet, that means we are talking about pure water things. Okay, and there is no salt involved in this, but in nature there are aerosols and the salts are available. But this is the study I'm telling very beginning when we have started 10 years before. And one thing, if you see the history, the DNS and all the concept came some 30, 40 years before, a theoretical concept. And that time also in 1890s, people have done some 2D study. But the 3D DNS first was done in 2001 in the McGill University, and that is also in the 80 cube or something, the grid points only. And that is very limited study, no temperature, nothing. It was done by Wellingford et al. In 2001. And after that, the 3D DNS we have started in 2010 and 12. So there was a gap of almost 10 years. And then we started doing studying everything in the 3D domain and 3D simulations for the cloud properties. But now you come to the point, the main question that how we are going to contribute to the either LES or the large scale models, because we are worried about to improving the large scale models, the weather forecasting models. So here in IITM we have come up with a new approach which is called the scaled up DNS. We cannot do the simulation as I said 4 meter cube or something, or even bigger than 2 meter cube or 1 meter cube. But we have come up with another idea which is called the scaled up DNS. This is really a PhD work. done my PhD. This is still going on. So here what we are saying, first we have to understand why we need to go for the bigger domain. So again, you see the cloud, this is a cumulus cloud. And if you see the height is also maybe it's half a kilometer or something. The width is very high. And what we are doing in that DNS, like 1 meter cube DNS is this tiny. But if you see the actual scale, we have so many scales in the turbulence and there are so many instabilities. So there is a multi-scale nature of the cloud. What we are actually doing in the DNS, we are going up to the smallest scale dissipative eddies, which is not known what is happening. But how much? Only that point, tiny point. What is happening here? What is happening here? We don't know. And we cannot simulate a bigger domain. So what is the approach? So we found an approach which is called the that keeping all the things as a real DNS as much as possible, no parameterization, but do the simulation up to the like LES grid volume or something like that. So we will not change any equation here, but we are going to do some kind of scaling of few parameters in the fluid property and the droplet property. So this is all, 5 years work with the PhD work. So we have changed the molecular viscosity using the actual formula. What is happening, like this is the new viscosity, this is the old one, and then this is the L2 and L1. L1, L2 are the size, the length of the DNS domain. It is a cube, so we are talking about one particular edge. So this is the way we are calculating, changing the molecular viscosity and changing the turbulent kinetic energy. So our idea is that we want to increase the domain size without changing the number of grid points. So suppose we have the 128 grid points or 256 cube grid points, we will keep only that much grid points. So the computational cost will be same, but we will keep doing the simulation in a bigger and bigger domain. That is the idea. Anyway, we have done this thing, but how we are doing? So one thing is that we have changed the fluid flow property, scaled up. What about the droplet? Suppose you want to go 10 meter cube. In the 10 meter cube with this number of density, how many droplets are these droplets? We cannot solve that many differential equations, set of the differential equation for position and velocity and like size. It is really difficult. So even we have done the scaling of the turbulent flow, kinetic energy and viscosity, we cannot do this. So we are scaling these droplets also, and this is called the super droplets. Super droplets concept is not new. This has come in 10 years before by some Japanese scientists. So what they are saying that we can consider a bigger droplets, call it super droplet. It contains many smaller droplets of the same property, like same size and all, and then each super droplets has a multiplicity attribute. It's called the mu. So the mu means it is telling that how many droplets are in a particular super droplets. So what will happen? Then we will take, instead of real droplets, we will take the super droplets and we do the simulation. So in this way, we will reduce the number of droplets. Okay. So finally, we are doing we can do the simulation in a bigger domain, but we are actually not doing the too much computation. Anyway, all those things we have, we can do this, all this, but before going to any further, then we have to verify with the theory as well. All this, scaling up, whether it will work, it will follow the turbulent theory or not. So what is this? One of the major metric for calculating is the 5/3 slope. So this is the real DNS, which we are saying that this is following the theory. Then we go 10 times bigger. Again, we are saying that slope is following 100 times bigger, 1000 times bigger. Everywhere we found that after the scaling, we are following the turbulent theory. So there is no problem as a theoretical. There is some loss in the energy, but that may happen in when we are going, but the small fraction of the TKE is losing. So this way, when we have actually got verified that everything is working, then we went on the simulation. Actually, this work is done and we have even published also. So then we did the simulation. This is the simulation we are comparing the TKE and the dissipation rate. So the TKE, this is in the real domain, then the 10 times bigger. So you see the real domain TKE fluctuation should be like that. In the 10 times bigger, we have a formula that when we there is a theoretical formula, this should be the actually the theoretical line. This should be the value. So we are getting the fluctuation within this line. That is always happening even up to the 1000 times bigger domain. The same thing we have found in the another parameter, dissipation rate. So this gave us the confidence. Yes, we are doing the nice scaling in terms of the fluid flow. Okay. So the another thing is that we have to also theoretically verify the droplet scaling. So in the droplet case, we have done the simulation into the 10 times, and we have gone up to the 64 meters, and we are changing the multiplicity. That is the scaling we are doing. So scaling we have done for like 100 multiplicity and 10 to the power 3, 10 to the power 4. So up to the 25 centimeter, we are getting exactly same fluctuation of, this is the basically standard deviation of the supersaturation. Supersaturation is the one quantity which is the responsible for the droplet growth, whether they will grow, condense or evaporate. So that is the one of the major metric to see the droplet property, whether we are going properly or not. So this is what we have done. And we found that, okay, up to 64 meter, we are no problem. We are getting the almost same supersaturation fluctuations. And so we are done with the scaled up DNS. And we said, now we can go for the in the meter cube, which was not possible even 2 meter or 4 meter. We are going up to the 64 meter. So what we are saying that in this figure, we are saying that changing the multiplicity, droplet multiplicity, provide the robust outcomes. So there is no problem. So this is saying that turbulence properties are fine. We are good, and this is a droplet property. We are good. So we have done the simulations. We did a lot of study in this. We published it. Finally, where we have reached. So I come back to that question. What I said in the beginning. How big domain we can go? How big domain? So if you see the real DNS, we were doing into the 1 meter domain and the sub meter domains. Okay, but the LES goes into the kilometer domains, and the the grid size goes into the tens of the meters and something. Now we have come up in between. There is a scaled up DNS. It's really very novel approach. So what we can say that now we can give a seamless information to at least the grid of the LES. So we can run the 10 meter domain or maybe 50 meter domain of the DNS, and then we can give the information to some of the LES, which is having a grid size of the 50 meter or 10 meter, and then this LES is really giving the information either to the general circulation model, GCM, or climate models, or there is some regional model, cloud resolving model. So they take the information from the LES. So who will improve the LES is the DNS. So this is what we have achieved. So if you see that we are just doing a very standard in terms of academic things, we are just solving those set of the differential equation, Navier-Stokes equation. Generally, it's like a CFD kind of study. But how we are applying to the weather forecasting, how it will be helpful for the weather forecasting. So these are the small scale problems, the issues which were not known in the large scale models. So all these things we have done for the cloud droplets. Like if there is a cloud droplets, then we can go up to this scaling. We can provide. So what information we can provide? Maybe we can provide the what will be the structure of this fluctuations of that TKE or dissipation rate. So we can do the DNS simulation and provide this information to the LES grid. What can be the size distribution, initially size distribution for a LES grid? That will be the output of the DNS that can go to the directly to the LES, and we can do a very good LES simulation for cloud or for the turbulent flow. So this is all about the cloud droplets, where we are talking about pure water. Okay. Next, I will move to the aerosol. So how the cloud droplet comes? We even going below one level down. So how the cloud forms? The cloud forms from the aerosols. Aerosols are salt which are available into the atmosphere. So aerosol can be different kind of aerosol on the sea. It is different in the city, seashore different. Above the sea surface it is different, and forest is different. Different means they may have the different size, they may have the different chemical composition. When these aerosols in the atmosphere, they get the supersaturation. They get from dry to become the wet. From the wet, they can condense and they can sometimes become the cloud condensation nuclei. That is called the CCN. And this is the problem. I mean, the research question here. When they will activate, once they become CCN, they are called the activated. Once they activated, they are no more aerosol, they become the cloud droplets. And from the cloud droplet, what we have seen, all those cloud droplet study, we are considering there is a cloud droplet. But how the droplets are coming into the atmosphere? That is still remains a question. So for that, we have a theory. We always have the theory for the theoretical things in the physics, but we have to do the numerical simulation for that. So any aerosol, when it crosses a critical size and the supersaturation, then it is called the activated. So this is the threshold point here. When it has reached that much supersaturation around the one particular aerosol, and it keep growing and reaches this particular size, then it will cross this barrier and it becomes the cloud droplets or CCN, cloud condensation nuclei, and then finally it becomes the cloud droplet. And after that, all this evolution, all this things happens through the condensation evaporation process, which we have seen before. But before that, there is a polar curve, and they call that one particular size. So if you see, I have seen that if they are in this area, if the size is less than R star, then there is a solute term dominates. So the solute is what kind of solute we have, what is the chemical composition, and if they are here, then the curvature, the droplet property will dominate. Then they will only grow through the condensation and evaporation. So overall question is that when they will cross this barrier, this depends on the critical size. And another question here is that the critical size and the supersaturation value is changing for each particular aerosol. So the dry aerosol, suppose has a small, so the smaller aerosol size requires more supersaturation to cross that barrier to become the CCN, to get activated. Okay, and the bigger size requires the less. So this is very complicated situation. When we take any see out any aerosol in the atmosphere, this can be any size, and this can be any chemical property. Chemical property also depends, change the supersaturation. Chemical property means suppose it is organic or inorganic. So if it is inorganic, suppose ammonium sulfate or sodium chloride, something, it has a different affinity, water affinity, which we call the hygroscopicity. So see, the complexity is coming not only physics side, it's also coming from the chemistry side, chemical composition. So not all the droplets, all the aerosol will get activated because of they all cannot compete and they cannot cross this barrier. Okay, the region that it depends how was it the number density. Suppose there are polluted conditions. We are talking about some within a city where we have pollution, we have so many different things, and there is a sample from the very clean forest where we don't have very much number density. So when there are number density is high and we have a particular fixed supersaturation, they are eating their supersaturation and growing. So when more number of the particles, they have to competition. So everybody will not get the enough supersaturation to cross this barrier. So that's why we call that not all the CCN activate at a time because of the activation and growth decrease as the S decrease, the S could be. When they are increasing, the S will decrease. The supersaturation will decrease because they will eat up. But we need a threshold value of the supersaturation. So this is what the theory. Now we wanted to do this, all this theory, we want to do the simulation. So how we will go? So initially the droplet growth is this, and the equation for the droplet growth is this, where S is the supersaturation This is the pure water we are considering, and K is the growth rate constant, which I told before. Now the droplet growth will change. I mean, this is both are almost similar, dr square over dt. So this is 2K constant will be there, but then supersaturation is the general supersaturation, and there is a droplet supersaturation will come in picture. But that is what is deciding the activation process. So this droplet supersaturation is basically depends on the dry radius and the wet radius. Okay, the dry aerosol radius. So in this case, we are not considering the droplet as a pure water droplet. We say there is a water droplet, cloud droplet, but there is inside aerosol. We call there is a seed. So when it is completely dry, it is just aerosol. When it acquires some of the moisture or the supersaturation, it becomes a droplet. Inside there is a salt. That salt property is required. So the RD means the dry one, dry radius. This is the wet radius. Then the surface tension, molecular weight, all these chemical things will be here. Molecular weight of the salt and all. So and the growth rate constant is this is standard for whether for this is the the cloud droplet or the aerosol. This is same. So the main change in the differential equation is only this. In terms of the mathematical, it is only that much change, but this requires lot of calculation for calculating the H drop at each time steps in our numerical scheme. Okay. So anyway, we have implemented this scheme. This change in the differential equation. And yeah, one more thing. This is the change in the differential equation for the droplet. But we have to give the supersaturation in the domain, which initially we were giving a fixed supersaturation at just like giving some kind of droplets. But here we have to keep the supersaturation so that they can actually cross this barrier. Otherwise, droplet will grow and they will eat up the supersaturation, and slowly the moisture will go down. What we have seen in our video in previous slide. So how we will keep the supersaturation in the domain? We are actually changing the stationary DNS domain to a rising partial domain. So in the temperature equation, in the Navier-Stokes equation frame, we are putting one more term, which is the vertical velocity. So this vertical velocity upward, we are giving the vertical velocity, and we are simulating or mimicking that the whole cloud, our DNS domain, which is basically a cloud, it is going up. When it is going up, temperature is going down, it is getting more supersaturation, because temperature and supersaturation are directly proportional. These two things we change in the differential equations in the main things, and then we did the simulation. Now suppose we have the code, we have our all mathematical model we are solving. Now we think about the physics, what kind of study we will do. So first we started doing the CCN activation of a single salt. We took like ammonium sulfate, and we did the two different kind of the normal the distribution of the aerosols. What are the distribution available? We can take directly from the observation, but as a theoretically, as a beginning, we are taking some kind of normal distribution, or just mono disperse also we can take. So we have first checked this mono disperse and normal distribution. We found that there is no change in the mean radius, but this may change in the activation process. So again, recall this graph that not all will activate, and only those will activate which cross this barrier, and they will cross the barrier when they get the enough supersaturation. And how we are giving the supersaturation? It's when the domain is rising height at a particular height. So if you see this figure very carefully, here the red one and yellow one are the unactivated at different height. So one is the height is 90 meter when it is going from ground, and up to 90 meter height we are getting the different size of the activated aerosol. These are the cloud droplets. So in the x-axis it is the CCN size, and here it is droplets. So if you see here, it is up to the 1 micron they have reached. This is the micron, and they are the 0.1. They were in the nanometer size. So here up to the 90 meter, it is activation is going on. Some are activating, some are unactivated, which is the red color. They did not get enough supersaturation. They could not activate it. So they are here still. Their size is below 0.1 micron. They are still aerosol. but we have got some kind of size spectra at the 90 meter. But at 200 meter, either all got activated or non-activated. So the blue color is all activated and the yellow color is non-activated. So here they have decided how many become the cloud droplet and how many will remain haze particles. This is really a very good application, application will go to understand the haze particles, cloud particles, maybe the fog later on, or maybe the air pollution quality also we can go. We have to see what kind of application we can do this. One of the simulation here we did, this is all like a one particular number density, like we can take a standard number density 120, whatever. But then we have done a simulation, the same kind of activity, but we have given two different number density. We call it the pristine condition or polluted condition. So here it is the polluted condition, here it is a clean environment. So there is some difference how the aerosols are behaving in a highly polluted area. So what will happen, I already told, when there are more number of density, like in a polluted condition, all will not get activated because they are getting some kind of competition. The super saturation is available a fixed quantity in the environment at a particular place, and we are just going up getting the super saturation. So you see in this case, in the clean condition, at a 200 meter, most of them got activated because they were less in numbers. Only just one point you are seeing unactivated. At the same time, here you see in the 200 meter, lot of aerosols got unactivated, the yellow color, the triangle. So this is what one particular experiment. So we have done many experiments. There's just two things I have shown. So we have done the experiment with the different number of the organic salt, not a single salt, like composition of the organic and inorganic salt, and then we are changing the vertical velocity to check how the velocity is impacting. So we are reaching 90 meter, we are reaching 200 meter, but what was the vertical velocity? It is 1 meter per second, 2 meter per second, 5 meter per second. Even now, recently the flight people are saying that this is just a very small velocity. In the flight, we are observing it is 20 meter per second. So what is the impact of the vertical velocity? That also we are actually analyzing. So if we can analyze this vertical velocity, again we can compare this numerical study with the cloud seeding experiment, which is really highly demanded right now. A lot of flight experiment is going on. So we take the research flight in the cloud, we observe some property, and then we do the seeding. And after the seeding, again another flight comes and then take the reading. So we will see that after seeding, how many aerosols got activated. We are triggering the activation actually by the seeding. So that is the one of the application in the future we can do. And we can tell that we can even tell to the experiment people that you should do that much exceeding and that time or that particular area. Many things can be done. Okay, so this is all about. I talked about doing the numerical simulation for the cloud droplets and aerosol, where we can apply it, where we can apply actually in the weather forecasting model. We can give some contribution. We can also compare the things with the observations. And now the next thing comes, doing DNS is really very difficult, it's computationally expensive, and then actually we are generating a lot of data. The data is coming not only from DNS, data is coming from the numerical weather forecasting model also. Data is coming from our flight observation. Data is coming from our laboratory, which are situated in many places in India. So a lot of data is coming, but we are not taking out the data. So first thing I have tried that we already have this data, the DNS data, where we have done some kind of the cloud property. We have done some information from the turbulence property we have seen. What we have seen, the turbulent kinetic energy, all like a safety kind of things we have done. But when we go inside the turbulence, there are another theory, like there is a vortex, and the vortex in the cloud or vortex in the ocean, it's really very important. And the vortex has a different property. So when we go to the any cloud, like this is the cloud we are saying, the turbulent, any turbulent fluid, they have the rotatory motion. So they have the high vorticity area. So now what the cloud physics community is saying that in general, any cloud we have a vortex area, and the droplets, cloud droplets go into the vortex, it has the different properties, and the droplets in the cloud, it has the different properties. So whatever we have simulated till now, we are just talking about a homogeneous kind of turbulent intensity everywhere. We are not worrying about where it is high or where it is low, but that is also an important question. So then what is the idea that instead of doing more simulations, we can go and dig out the data. So we can dig out the data using some like a data science algorithm, some machine learning algorithm we can apply. So we can find out how the turbulence is impacting the spatial distribution of droplets. So whatever the size distribution I was talking about, like mixing size distribution or whatever. So how the turbulence is affected. I mean, we can do the turbulent effective, we can do many simulations, and then we can say high turbulence density and all. But I'm saying that within the data, we can also do the same kind of study. So how the spectral properties are changing. So when we go to the high vortex area and low vortex area, how the droplet properties are changing. So this is not all of a sudden. Actually, some 22 or 2 decades before, some theory came. The Raymond Shaw et al. They are from the Michigan Technology University. So he's a big professor in physics. He has said done some kind of foundation in this vortex calculation. But that time there was no DNS. Okay, so he has done some kind of study using the whatever the I think partial model using the Raytheon vortex, and he declared that in any cloud, half of the area is the high vortex, half of the low vortex. Okay, but as I said that later on, Wellington he did a first DNS during 2000 and 2001, and he also did this kind of study. It was a small domain, but he was not agree with that half of the domain is half of the area is the high vortex. Okay, so like we are all working with together with this Wellington and MKAU. He is also a professor in McGill University. Wellington was the postdoc that time, and so it was they all were working together in the US. But you see, from 2000 to till 20. Last 20 years, there was no extra work was done. When we have done this 3D simulation of the 3D DNS, all those people were involved, and Shaw et al., Raymond Shaw and MKAU, they all were there. But suddenly this came in our mind, like we have not touched this area. So MKAU told, look, why don't we see these properties? And then we have done this idea that we take the DNS data and we started finding out the low and high vortex region. We tried many things, then we went to the machine learning algorithm. So we tried the unsupervised algorithm, k-mean clustering. So what is k-mean clustering? Maybe people might be knowing. This will make a cluster of the different regions. So we have to decide what intensity we want to take. So we are calculating the vorticity first from all the data. UVW, we are calculating the vorticity. In the vorticity data, we are applying the k-mean clustering. So actually, this algorithm cannot decide the optimum value, which value we want. So we have to give some value. So we did a lot of data pre-processing part, and we found that much intensity we want. We will decide this is the high vortex area, this is the low vortex. And then we did so many clustering exercise, and we decided that particular number of the clusters are required to know a good region of the high vortex region, like we are saying here. So we have done many experiments. Finally, we found that this is the area, is the high vortex area. So what we have found actually, Raymond Shaw said that it is half, and Wellington et al. In 2000 they said it's not half, it may be different, and we found it is only 2%, not 50%. So only 2% area is the high vortex. And that was like validated with many things and all. And finally, we did the study of the droplet property, which we were really waiting. And these kind of study actually people are doing in the large scale domain. So when they have the ocean simulation or any atmospheric simulation in the many kilometer, and they found the high vortex region is a few kilometer area, and then they want to study what is the property of the cloud or what is the property. So that thing we have done in a small tiny DNS domain. It's all real domain we did, and later on we can even do for the scale up domain as well. So we have found that when we have a high vortex region, it has a low number density. Well, this is expected. So vortex is like this kind of fora. It has a very high balance rotatory motion. So any droplet which come into contact, it will go inside, but then it will be thrown out due to the centrifugal force. This was we were knowing, but now we are saying yes, it is happening. If you go and check the high vortex region, in the high vortex region, we are getting low number density. Less number of the droplets are found there, and their size is also less. Because there is a temperature difference, there is less supersaturation, they are not growing much compared to the other area. So like in this area, they are growing much, but the high vortex area, they are not growing much. So this kind of study, what is happening in the high vortex region and what is the property of the low vortex region, this all are matching what we expected in theory. So this is also a very good study. We have already published this thing in the atmospheric chemistry and physics. So in 2020 it is published. So this is all the conclusion from that machine learning approach. Applying this is just first attempt. We can still go for the bigger domain and a different kind of study can be done. Okay, so I will say that maybe I can summarize now what has been done into the DNS. So first thing we have done is studied the droplet dynamics in a simple isotropic turbulence, starting without as a constant temperature, and studied the droplet size distribution and phase relaxation. Phase relaxation time means whether the phase will change or not, whether the droplet water will evaporate or condense or not. That is the phase change we call. And what is the mixing? The mixing, what is happening in the natural cloud, whether it is homogeneous or inhomogeneous or extreme case, that also we have done. We studied using the DNS and all kind of turbulent properties, how the kinetic energy is changing, which all the results I have not shown, but I'm saying that we have done these many things. We have compared the observation data. Actually, we are also comparing things with the lab experiment. One lab experiment is being done by Raymond Shaw in Michigan Technology. He's having a very big cloud chamber. So that also a simulation we are doing through the scaled up DNS and real DNS. Another experiment is happening in ISC Bangalore with our collaboration in the mechanical engineering department, that they also have a cloud tube and they are generating, that is going on. So we are actually, it is very difficult to do the similar experiment as a DNS or do the similar DNS as a lab experiment, because we have limitation in the boundary conditions. Our DNS is having a triply periodic boundary condition, but that is not happening in a cloud chamber. The droplet sticks into the wall. So that kind of boundary condition we are not able to mimic, but it is going on. So observation data we have done already, and we are still trying to do the comparison with the observation of the aerosol. We have done the observation of the cloud droplet. So we have our own laboratory here near to Pune. It's Mahabaleshwar. It's a very high altitude laboratory on the hill. So we are observing the clouds, and then we are seeing the property, inorganic, all those things we are going to compare it. And that is for the basically the aerosol dynamics, aerosol comparison we will do, observation of the aerosol activation, everything we can observe through the probe. So we have actually done the simulation of the aerosol dynamics, the simulation of the activation of the different environment conditions. This we are going to validate soon with the lab observation, the ground observation. And we have came up with a very nice idea, a novel approach of the scaled up approach, which is just recently in the last 3-4 years. And this approach is basically providing a way to get rid of, to do the very nice subgrid level parameterization or improve the LES, which is giving a way forward to improve the weather forecasting model also. So as you can see that we have validated with the numerical things. And the next thing is we have also done some kind of the turbulence properties, high or low vortex, which was actually we not knowing before in the large scale model. And so we have applied the machine learning algorithm in this case, and we investigated different regions. So this is the sum of the things I have told, because everything is not done in one talk. And in future, like all these studies, what we have done, it in just like a droplet interaction and all, and condensation, evaporation, activations. We did not talk about the collision and coalescence. So till the cloud droplet, it is fine till the 20 microns, because the collision and the condensation is not much important for the cloud droplet, but in the aerosol it is important. But when the rain droplets falls, it happens more, 50% things happens because of the condensation and coalescence. So the droplets grows through the condensation, then they collide, then they become bigger droplets, and when they reach the size of the 100 micron or something, they become the raindrop. And then once it becomes the raindrop, then it depends on the environmental condition, they can precipitate. Same thing happens in the aerosol case. Aerosols are activating. We have done a study how the turbulence is affecting the aerosol activation. But we have not considered the collisions. Collision is also activation. So turbulence is also affecting the collision. So all they are interrelated. So once we have the collision things in the code, we can again study how the things are changing, how the activation and activation fraction, unactivated fracted particles, what we have seen is whether they are changing or not. And in the cloud, we don't have any, cloud droplets, we have the ice particle. The ice particle is difficult to model, but they have already started, Japanese people and some US people, they are doing the DNS for this. And the DNS in the ocean, like there is a ocean surface, if you see this from the surface to 1 meter, a lot of mixing is happening. The mixing of the different layers, that work can be done through the DNS. Even some people, ocean scientists, they are asking. And the linking between the scaled up DNS and LES. I said that scaled up DNS is useful for LES, but we need to do it. Exactly what we are trying to do, what we can do. That is the work which can be done in the future. And it's really a very good problem. Maybe the next PhD students can do this. And investigate more turbulence property in the cloud. So turbulence, we have started working towards the high vortex and low vortex region, but there are many other things which the cloud physics people want to know and they want to do it. That can be done. And another thing, what we can provide directly from the DNS to the either LES or the model is the entrainment rate. This is the one parameter which decides the rain formation in the precipitation formation in the model. So whatever the entrainment rate, that means how much the environment is entering the cloud and how much going out. That basically decides the precipitation formation in the model, and that we don't know. Right now it is just all approximated. But once with this rising parcel DNS is working as a going up, we can take the DNS going up to the 1 kilometer or something. That is enough to get the entrainment rate in a cumulus cloud or some other cloud, and we can give the information to the LES, and we can calculate that parameter which called the entrainment rate parameter. This is something recent, the future work which can be done. And I think it's enough for this talk. And I would like to thank the people, the group here in IITM Pune, like PhD student, Lois Thomas, Dr. Momita, one master student, Rahul Ranjan, scientist, Dr. Sudarshan Bera, and my collaborator, like George Schumacher in Germany. We have started work in 2009-10 in Germany when we first published this thing like how the DNS will do 3D DNS. Obviously, Raymond Shaw was always together with, because he started in 1998. All these things theoretically and the lab experiment. So we have worked together till now. We are working with him. And Man Kan Liao, he is known as the father of the cloud microphysics. He just last December he retired, I think at the age of 75 or something. And Andreas is the young professor in the McGill University. And Wojtek Grabowski is a very senior scientist in the National Center of Atmospheric Research in USA. He has worked a lot with us. In many things he has supported us, and he has given. He's a very big cloud physicist in all over the world, a very renowned person. So he has worked with us, and that's all. Thank you. I think I have got 1 hour 20 minutes.
Yeah. So participants, do you have any questions? You are free to ask.
Hello, sir.
Yes.
Yeah.
Good afternoon, sir. Sir, I am from mathematics background, working in differential equation. So my
Yes.
question is, from where can I start initially to get to know about this topic through mathematical and mathematical aspects about the same?
From where you should start? I have shown some set of equations here. Okay.
Yes, sir.
This is what the mathematics equation, and I told that I have applied a numerical scheme, only second order scheme. But people can try the higher order scheme, but it is not very much beneficial or not beneficial or beneficial. We don't know right now. So
Okay.
if we go for a higher order scheme, we can do. And this is the basic equation. Once we go for the aerosol equation, we change the equations. So we are doing just as a physics people, we are not worrying about any numerical analysis behind that. We are just changing the equation based on the physical formula, and we are running the simulation. But if you want to do some pure mathematics things, you can go the differential equation, see whether it can feasible to do the higher order schemes or not. That is the one thing. Okay. And if you want to do some kind of data analysis, data science, that is also a lot of scope in that, applying the machine learning. And I will just say that if I have any other equation, when I change this temperature equation, look at here. The temperature equation, we are changing this to put the vertical velocity. So the vertical velocity, like initial, this is the flow, and this is the equation. We are changing a lot of things, but we are not doing any kind of the numerical analysis here. So whether, I mean, this is, you have any scope, I mean, as a mathematics, you can tell whether you can do this. Otherwise, you can go into the simulation. You can also try to do some kind of DNS. If you want to do more cloud physics or something like ocean science or something, there is a, I said, stratification is not being done. So how to add this stratification in this equations, PDEs? Okay, and in the droplet case, cloud case, we have the phase change. Phase change means we have water and vapor. In the ocean, we will have the salt and the water and salinity, different salinity, and how the gradient is changing. So there are the things we have to little bit know about the physics behind it. Did you get the point?
Yes, sir. Yes. So, thank you, sir.
Yeah. Any other participant?
Hello, sir.
Yeah.
Yes.
Sir, you are using this term
Introduce yourself.
microphysics.
I'm sorry, Tane. Just 1 or 2 line, like you can introduce yourself.
Oh, sorry, sir.
Yeah.
I am Kumar. I am a research scholar at IIT Guwahati, working on multi-scale modeling.
Multi-scale model, okay.
So, sir, my question is, you are using this term, microphysics. So, how are you bridging in between macro and micro?
How I am reaching?
Yes.
So I am working only in the micro. Micro means you see that I am talking about each and every droplet, each and every aerosol, and we are talking about the Kolmogorov scale of the flow. This is all at the micro scale.
Okay.
But you said that you are working in the multi-scale differential equation.
Multi-scale model.
In this case, I will say that I am using a time step delta t, which is same as the fluid flow and same as the droplet equation. This is not correct, which is taking, not correct means it is really not very good strategy. So the fluid flow has the CFL condition, it can have a different delta t, and we have to take a time iteration based on the fluid flow. So the delta t comes from that fluid flow, but the droplets, especially the aerosols and all different size of droplets, they don't need many iteration, or they need even more iterations. So how you can go to the multi-steps, that can be done in this numerical scheme. Instead of one single time step, we can go multi-step based on the droplet size. I mean, this is one way people are trying here also. And if you want applications, you can go to the application in the cloud microphysics and all. I don't know what area you are working.
Sir,
What problem you are taking?
right now I am working on theoretical aspect on equation-free multiscale modeling.
Yeah, so I mean, if you have time, what is the stage of your PhD? You can apply this your theoretical things into some of the applications.
Yes, I have some plan to apply those on drug delivery.
Apply in
Drug delivery.
graphically waves. Huh?
Drug delivery in mathematical biology.
Okay. Yes, yes.
So that means your total output is in micro scale.
Yes. Currently it is microscope.
Okay. Okay, sir. Thank you.
Yeah, any other participant? Okay, please come. So yeah, so Bipin,
Yeah.
we have one student. You can just
Yes.
Good afternoon, sir. Sir, my name is Tarang Soni, and I am a BTech second year student. Sir, I was having a question, sir. As you said that in a high pollution areas, the aerosol activation is comparatively less, right, sir? So, will it have, sir, can you please explain what effects will it have in the climate, weather, climate or weather of that region, and if it will be having any long-term effects? And sir, if it is having any negative effects on the climate, and and
a little slow. You just
okay, sorry, sir. Sir, I will repeat my
question. One or two question, one by one. I can go. You are saying that in a polluted condition, the all the aerosols don't get activated. That is the one question you are saying, no?
No, sir, my question was what effects will it have in the weather or climate of that region?
I mean, on health region, both are different. Health region is different.
Climate and weather of that
climate
region.
and weather. Please,
Weather
okay.
of that.
Climate and weather.
Yeah.
So, see, this is just a thing when you do any kind of the run the weather model, you are giving some kind of the number density of the aerosol, some kind of number density of the cloud droplets. But this is all theoretical. Okay. You don't know what is the fraction of the activated and non-activated in a particular area. They even don't worry about what is the chemical composition. And they have to run the model because they have to run the model for the whole area. So we have a gap from the large scale model to the actual things happening in the small scale. So these small scale processes were not known and people were not working maybe in the last 10 years they started working. We did not have the computers before to run the, like I'm running the DNS, I'm using sometimes 30 or 40,000 of the cores and running for a month at a time, which was not possible before.
Sir, I was asking about the effects in the physical environment. The effect of less aerosol activation in the environment.
I cannot answer the fully here because I'm not working in that domain. But suppose there is a polluted environment, okay, and there is a cloud, there is some environmental condition, and all the aerosol did not get activated. They could not become the cloud droplets. Once we don't have enough cloud droplets, we don't have the enough interaction and all, they will not become the rain droplet. So in that particular area, precipitation will not happen compared to the pristine condition where we have a very clean area.
Yes, sir. Sir, I could also infer that the rains will decrease in that area. So,
Yes.
sir, is there a way that we can artificially activate the aerosols which were not able to get activated?
Yes, we are doing. That is called the cloud seeding. That's what we are currently doing in the Maharashtra area. Our flights are going and doing the active cloud seeding.
Okay.
Then the question comes to how to do the cloud seeding, what is the chemical composition, what we should do. Currently, we are doing whatever the company is providing, our institute is doing. and we are succeed. Many government is state government is taking our suggestions, and scientists are going there and telling how to do cloud seeding. A lot of things are happening in the drought area. So that's we do. So what is happening in the seeding? Basically, we are triggering the activation. So there is a chemical composition in the aerosol. We are giving another chemical composition which can trigger the hygroscopicity. It can increase the hygroscopicity of that particular solute.
Yeah, yes, sir. Yes, sir. My doubt is clear now. Thank you so much, sir.
Okay.
Thank you. Thank you so much, sir.
Yeah. Any more participant want to ask? Okay, I have one quick question to you, sir.
Yes.
So this cloud physics is involving bubbles, droplets, and particles. So are you
It's droplets and particles? So bubbles is different thing.
okay? Okay. So you are using mixture model.
Mixture of
Yeah. So some fluid flow model something.
yeah, we have the turbulence fluid flow, and apart from the fluid flow, we have the Lagrangian particles also. So it's like a particles in the turbulence. So they are coupled to each other. So how they are coupled? I will show you that in the temperature equation.
Yeah.
Can you see the slides? No.
Yes. Yes. Yes.
So if you see this red one here, there is this condensation rate CD in these two equations, temperature and humidity. Okay. This condensation rate is coming from the droplets.
Okay.
So within a grid, each grid we have like 8 corners. 8 corners we have the value of this fluid flow, turbulent flow. But then this condensation rate is giving feedback from the droplets. So all the droplets together, we are calculating the condensation rate, and then we are giving reverse interpolation value, giving the value to each grid point of this equation Q and T. So this way they are combined and they are coupled to each other.
Okay. 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 Yeah. Yeah. Thank you. Okay. Yeah. So if there is no more questions, let us thank our speaker. And yeah, thank you, Dr. Bipin, to join us and give us a weather forecasting model, and with some using this differential equation, and having a glimpse on how the machine learning also helps you.
Yes. So this is all machine learning I have applied, and we are applying many other things.
So okay, so you are generating the data from these equations, or you are getting the data and then fitting it?
No. This is all DNS data.
Okay, fine. Yeah.
That is what the question initially we thought, because when we these very senior people, and 30 years before they have done some kind of calculation on the 2D models. Now we have the 3D models, and they have found that this is the high vortex region, and they did some kind of study. I saw the paper in 90s paper, and the same person who wrote the paper, and Grabowski and MK, they told that can we do it in the DNS. So we started doing this.
Okay. Yeah. Thank you, Dr. Bipin. Yeah.
Okay.
Thank you, sir.